Many thanks for the introduction and more generally for the invitation and the opportunity of giving this talk. And yeah, thank you all for logging and your presence here. Just give me a sec. I will try to. Okay, are my slides visible? I hope they are.
Yes, they are. Mm-hmm.
Yep.
That's great. Okay. So let me begin with a quick overview of what I'm going to talk about. I mean, I start with an introduction. Obviously, I present some notions, some definitions which are going to be used later on. Then I'm going to present results of a paper which appeared in Bayesian analysis, which concerns a very specific example of Bayesian mixture model and the behavior of MAP in that model. I mean, in a moment I will explain what those things mean. Afterwards, I'm going to present some attempts at generalizations of some of those results. And finally, I'm going to briefly discuss an idea how to of some applications of some byproducts of this theoretical analysis. I mean, this will be made clear later on. Well, now today I did some say Monte Carlo simulations of this presentation, and I mean I would say that it should last for approximately 40 minutes. I mean, the sample size was very small, so the variance is very big, but I guess we have plenty of time anyway. So in case of any questions during the presentations, I mean, interruptions are very welcome, and I think there's no hurry. So please do interrupt in such case. Now, the basic statistical problem we are going to touch is clustering, so you all know what it's about. Now our approach is Bayesian, and there are several ways how you can express this Bayesian approach to clusterings. In my research, in the context of my research, the most natural was the following. Okay, a partition clustering is something unknown in this case. So in a Bayesian approach, we put a prior distribution on this unknown thing. So I assume that this partition structure, this clustering, was somehow sampled, and I put a prior on that partition. And having this partition in my hand, I want to know, okay, what is the conditional probability of the observations given that partition? So I mean, a natural idea is often to assume that within clusters, the data are spread as Gaussians. I mean, it's not an only choice, but the one which is very tempting. So how could we express this desire to model data as Gaussians within clusters? We can say that, okay, now, firstly, when this partition is somehow obtained by this random process, then for every cluster, I sampled the center of this cluster, the mean of this cluster. And afterwards, for every cluster having its mean, I sample the observations within that cluster from Gaussian distribution with this given cluster mean and some hyperparameter covariance. Okay, so for assuming that in every cluster the covariance is the same, here we would put some hyperparameters. And if such a model is specified, our Bayesian approach for inference is to investigate the conditional distribution on the space of possible partitions, given conditioned on the observations that we see. What about, I mean, here I presented how can you construct likelihoods, a very natural approach. I mean, the probability distribution of observations given the partitions, we would have to just to integrate out those theta subparameters, say. And what about the prior distributions? What are prior distributions on this vast space of partitions? A simplest example, I think, is so-called Chinese restaurant process. So how it's constructed? Well, we need a parameter alpha, and I'm going to show you what would be the probability of such a partitions of numbers from 1 to 7 in the Chinese restaurant process. So imagine that those numbers are customers in the Chinese restaurant, and the clusters are tables. So we assume that, okay, every new customer chooses a new table with probability proportional to alpha, or he or she joins a new table with probability proportional to the number of people sitting there. Okay, so the first customer does not have too much choice, but the second one can either join the first or choose a new table. We can see from these partitions that he chose to join the first customer with probability proportional to 1, the number of people sitting there. So the norming constant is 1 plus alpha, and this is the total probability. The third customer, we see that she chose to sit by another table, and this was done with probability proportional to alpha, which gives probability alpha over 2 plus alpha. This process continues, in the end giving us the probability weight of such a partition of numbers from 1 to 7. Now,
I have a question. So is it alpha is not dependent on current choice in the past, so it's set once for good?
Yes, exactly. This is a hyperparameter of our modeling approach.
But it's still kind of struggle. So it's because normally I think it was like it is 1 over the number of individuals already in the restaurant, or I'm missing something.
I mean, 1 over number of individuals plus
already.
alpha. I mean, this alpha always is the norming constant.
Oh, okay.
Every time. But if you want to compute the nominator, you have a choice, either alpha or the number.
Oh, okay. I follow it. Yes, thanks.
Good question. Yeah, all those things sum up to the denominator, so it works. Thanks for this question to clarification. Okay, so as you know, as in Bayesian approach, we are interested in the posterior distribution in this discrete space of partitions given the observations. And yeah, this conditional probability is proportional simply to the product of the prior weight and the likelihood. But as is very common in the Bayesian setting, it's not possible to compute the norming constant in this case, and that is why when we use this kind of models, we need to do some approximate sampling like MCMC simulations. But now, I mean, setting those technical problems aside, imagine that those important, surely technical problems aside, imagine that we are requested to give an estimate of the partition structure. And what is the natural choice in this model? Well, supposing that I somehow computed that one, I mean, an estimator, like reasonable estimator, would be to choose the partition that maximizes the conditional probability. But I mean, this is one computational problem less with this approach, because a partition that maximizes that expression is the same. I mean, maximizing this expression is equivalent to maximizing that expression. So at least theoretically, we can ask ourselves a question, okay, what about the behavior of so-called maximum a posteriori estimator? I mean, the partition that maximizes the a posteriori probability. So this model I've just introduced with the Chinese restaurant prior on the space of partitions and this double Gaussian likelihood with fixed covariance for every cluster was the object of analysis of the paper I mentioned before. And now I briefly will describe the main results of the paper. So the basic one is that in this model, the clusters in the MAP partitions are always linearly separated, which means that every two clusters, suppose that those figures are the indicators of being in one cluster or another. So for every two clusters, I can find a line, or more generally, a hyperplane that separates these two clusters. And it's equivalently, we can say that convex halves of data within clusters are separated, are disjoint. This formulation will be of some importance later on.
Another question. Question, yes. So the T, I'm covariance T. I mean, this is so it's an arbitrary. I mean, what about these parameters with covariance? I mean, do you estimate them or?
Yeah, thanks for that question. Forget to say all those things in blue are unfortunately hyperparameters. So this is something you set in. I mean, in ideal Bayesian world, this is something you set in advance without looking at the data, because this is like specifying your model in ideal world. You shouldn't use data to estimate this parameter. But practically, I know there's like the huge trend, and it's understandable. I'm not sure, perhaps it's called empirical base. I mean, using data to adjust your Bayesian model. So actually, in practice, usually take some knowledge from data in order to estimate it. But we are in the ideal world, and actually, those are things that you set in advance without looking at the data. Those in blue. Does it answer the question?
Yeah. Can I ask another question?
Yeah, of course.
So they're linear. Is that due to they have the same covariance matrix, right? Otherwise, they could separate in other than linear ways. Or am I misunderstanding?
Sorry, could you repeat? I had some.
So when we have the same covariance, is that what makes them linearly separate?
It's a perfect question. Thank you very much for it. Yes, it is, and we'll learn about it in a moment. I mean, because of that, indeed, the fact that we assume our modeling assumption is that within every cluster the covariance is the same. This is the reason why those clusters are linearly separated.
Okay, but then I have another question. So, but the number of elements in the cluster is preset, right?
No.
I mean, conditionally on the prior sample from the prior.
No, it's not. I mean, the prior is on the space of all possible partitions.
Yeah, but if you have a partition,
yep,
then there are different size of sample, right? For each cluster.
I mean, there are possibly each cluster has a different number of observations. Yes.
Exactly. So how you can have the same covariance?
I mean, it's a theoretical. It's an expected covariance.
I think the covariance is for each of the elements in the cluster.
Yeah, the covariance. Thank you for that. The covariance is for each element of the cluster. So within each cluster, I sample the observations within this cluster IID from this distribution, and that the covariance parameter is the same for every cluster. I'm afraid that does not answer your question, but
yeah, okay, I understand. I understand.
Maybe
I will come back quickly to this. Yeah.
But Lukasz, I do have another question. Sorry.
Yeah.
So, what is the? I mean, it's the first time seeing it's. What is the connection to LDA, like to linear? If you do maximum likelihood instead, so it's also, you know, assuming the same covariance, it gives you linear separation, hyperplane separation, right?
Yeah, I mean, I think if you did just the
Just asking if it's some kind of conjugacy of this CRP to the the classical Fisher linear discriminant analysis.
There is a connection, and actually we have 2 slides about this connection. So maybe let us move on to these slides, and if then there will be questions, I will happy to answer them.
Sure.
So sorry for
Thank
cutting
you.
this at
No
the
problem.
moment, but maybe just a quick glimpse at this picture and this model. So how it works, I randomly choose a partition of indices actually. This is how I imagine the data was obtained. I randomly partition indices. Then for every cluster, I sample the mean. And when I have means conditioned on these means, I sample the observations IID from non-bar distributions with this mean and some hyperparameter. This should be the sigma in here, which is the same for every cluster. So actually realizations of this modeling scheme would be kind of the same, look like the same ellipses in a way spread in space. Okay, so this was a recap of how we model the data, how they are obtained.
I just want to make sure, even if you observe the theta k, the theta I themselves without noise, not the x's, the thetas, there would still be a clustering problem, right? There's still a posterior distribution over the clusters given the thetas.
Of course, I mean, it's still a posterior distribution. And what I do to summarize it, I mean, it's of course, as a Bayesian, I should stop my analysis at saying, okay, this is my posterior distribution. I sample from it in order to kind of do some presentation how it looks like. But say what I requested to do is to give an estimate. So my estimate is the Bayesian. I mean, my estimate is to choose the one partition. I mean, possibly there are more of them, but any partition that maximizes the posterior distribution, I somehow computed.
Yeah, sounds good. Thanks.
Thank you very much. I hope that it really sounded good. It's not only that you are very very pleasant. Okay, so let me move on to another result. And this is something I could call, say, frequentist validation of the MAP procedure. And what I have in mind is that now I suppose that actually my sample is not coming from the model I presented before, but it's an IID samples from some distribution P. And what I'm going to do is yeah, I'm asking questions about what are the properties from this MAP approach to estimating the posterior when my data is actually an IID sample from some distributions which I call P, the input distribution. So actually the problem with this MAP is that, okay, potentially, say I've got a sample of 100 points. This is the MAP, and yeah, the convex hulls are disjoint. This is linearly separated partition. And so the problem is that potentially adding new points can significantly change the partition. And there are several natural questions you can ask in this setting. For example, what about the cluster size? Is it that at some stage you have like a fixed number of clusters whose number increases somehow, or perhaps every once in a while you obtain some tiny cluster, something inside, just because of the randomness in this procedure. So we partly answered that question about how the cluster sizes of the MAP behave, but in a restricted setting. And what is the restriction? Namely, we concentrated on the clusters that intersect a prefixed, I mean a ball fixed a priori. So at the very beginning, I fixed a ball in the space and take track of only of those clusters that intersect that ball, that have at least one point in common. So those are colored clusters. And our finding was that in the built assumptions on this P, the size of these colorful clusters is proportional to the number of observations. So we cannot eradicate the possibility of obtaining small clusters in here, but what we know is that if they appear, I mean, further and further from the origin in some sense, because if I fix the ball, those balls that are intersecting that ball, their size is kind of controlled by the size of the sample. So this is the first result. Now let me change slightly the view on that topic, put this MAP aside and consider a much more simpler approach to partitioning. Namely, say we arbitrarily at the beginning chose a fixed partition of the observation space, as in here. And now we take IID data and partition them according to this initial partition of the observation space. Okay, so obviously I can read these partitions as, okay, 1 is in one cluster, those 3, 4, 6 are in the other, and so on. This is something I will call induced partitions. They are induced by some a priori chosen partitions of the observation space. And well, as a partition of indices, I can assign to them this posterior probability, but not in this scheme, but in this reasoning machinery I introduced before, this posterior from this Bayesian model I introduced before.
What is this probability?
This probability is took from this Bayesian model. Okay, this
Oh, it's the probability of getting this partition, posterior probability of getting this partition.
Yes, but of getting this partition, but coming back to this model I introduced at the very beginning. Okay, so I have some way of obtaining partitions, but I score them using the this posterior weight I introduced at the very beginning. This posterior weight, I mean, maximizing this posterior weight is getting the MAP. This call function say. Okay, so now what I do is sample size, and what I want to do is to do some estimation of this guy in here. So how it approximately behaves. So I will take the nth root of this guy in here, while n is the number of observations. And I mean, this is a straightforward computation, leads us to this this expression. I mean, if I take induced partitions on an increasing sample, take the nth root of that, I can get a limit, and those are like straightforward computations using strong law of large number. This blue bit, this entropy looking like bit, comes from the CLP weights, this prior, and this expected square is coming from this the likelihood, the Gaussian likelihood. Now, how to join these two bits together? Well, I mean, the whole idea of considering induced partitions was taken from the following question. I mean, okay, I introduced the sample size, the size, this independent sample, and I track the behavior of the MAP partition in my reasoning machinery, in my inference machinery. So as the sample sizes increases, we notice that those convex chunks more and more tightly fill the space. And as, okay, those convex hulls are always disjoint, and the points are spreading over the space. So we can expect that somehow in the end, this should give me a picture that fills almost all space. So actually, you can think that in the infinity, I expect that this should, if it stabilizes, it should give me a partition on the whole observation space. That's why I introduced this reverse optic on the previous slide. And putting that way, I mean, it's not surprising that actually, if the limit exists, it should be a maximum. I mean, if this limiting, say, if the limit of the convex halves of clusters of the MAP partitions exists, this should be connected to the partition of the observation space that maximizes this delta P function. So there's a connection between this MAP approach and partitions of the observation space that maximize the delta function, this limit function I mentioned before. I mean, you can ask in here, okay, limit in what sense, and so on. I mean, this is a very rough formulation. You can see in here. I mean, the limit is in the sense of metrics on convex sets. I mean, firstly, both on Hausdorff metric and more on the symmetric distance metric as I connected to this distribution P. But let us put that aside. In some sense, there are limit points of this procedure of taking convex halves of clusters of the MAP partitions, and each of the limit points must be a partition that maximizes this delta function. In here, I must also underline that we obtain this result in a very restricted setting, unfortunately for input distributions with banded support, but I mean, we hope to extend it and still hope, but didn't manage to do that.
Just to make clear that the P in this, it is the distribution from which you sample your data, right? IID.
Yes.
So it's IID. So and there's no, I mean, except some kind of basic assumption, it's not restrictive on this distribution.
And apart from being continuous with respect to Lebesgue measure, no. But yeah, this part in here is very restrictive because actually this P is in this sense not from the model, because the distributions you get from the model are mixtures of Gaussians, so they have infinite support. So I mean, this is, you can say, inconsistency result. Inconsistent in the sense that those P are not taken from the model anyway, but still I think it's informative to some extent, and I hope that you can actually extend it, but I weren't able to do so. Okay, so let me speed up slightly, because now I'm sure that my initial estimate was going to be negatively biased. So now I ended the part where I presented the results of this article and describe how we managed to extend them, or rather prove them in a bit more general setting, at least some of them. It's a natural extension of the initial model is, okay, firstly, instead of assuming that within every cluster the covariance structure is the same, we can say that we also sampled the covariance structure, the covariance within every cluster from Wishart distribution. And more generally, we can consider a model where the distributions on the component parameters and the distributions of observations within components are both coming from conjugate exponential families. So I'm usually seen these writings many times before. Just to introduce the main characters, main heroes of the what is going to happen next. I mean, this is the sufficient statistics of observations. Those are two log partition functions. This one is for parameters, this one for observations. And so this is how we generalize the model in terms of likelihood, how we generalize the model in terms of the prior on the partitions before those were just Chinese restaurant process. More generally, we consider exchangeable random partitions. So you can think of them as a probability weights on the partitions that are invariant with respect to the permutation of indices. And via some infinity kind of theorems, you can present the following general way of obtaining exchangeable random partitions. So you need to have a weight to randomly sample segment 0,1 into subsegments. So say you sampled a division into subsegments. Then in order to obtain a partition, you just take a uniform sample on this segment like that, and you read the partition in here, okay, 1, 3, 5. So indeed, when you have a way of sampling, getting a random division of segment 0,1 into subsegments, then you can translate it into a random partition of indices. And indeed, both Chinese restaurant process and more general Python ER process, I mean, those are examples of exchangeable random partitions. But I mean, for us, at least for this result I'm going to present now, the only important thing was that those probability weights are symmetric in the sense of they are invariant with respect to permutations of indices. And now this separability results presented earlier, that one with the linear separability of clusters, generalize to the case of conjugate exponential family in the following way. Now the clusters are separated by the contour lines of linear functionals of T, which means that when I have, I mean, for every two clusters, I can find the line of this form defined by this equation that separates those two clusters. So indeed, for this first normal model where the covariance was the same for every cluster, this gave a normal, I mean, the linear separability because the sufficient statistic is linear. And then for the, I mean, this is referring to one of the questions. Indeed, when we allow the covariance to be different for every clusters and it is sampled from the V-sharp distribution, then the separability is quadratic in the sense that every two clusters are separated by a surface of order 2. And now, thank you very much from this earlier comment. Indeed, this is what I like about this result. It's an analogy from the same thing about the Fisher discriminant analysis. I mean, this is a classification, not clustering, but still in this setting, if I have two samples that I know what are the labels, and I have a new sample, I want to assign to one of these groups. If I assume that the covariances are different, then the learning curve is quadratic. Otherwise, if I estimate the covariance structure as the same, I have a pooled estimate of the covariance structure, then the separation, I mean, straight learning curve. But I mean, indeed, those results are different in the sense that that result is indeed a simple computation, and the similar one from the classification is a bit more involving. And let me show you the only proof in this presentation. I mean, this is a proof of lemma to which actually the whole separation theorem boils down to, if viewed from a good angle. So yeah, it's stated formally in here, but please bear with me with this example. So what it is about? Well, I have a number of points in RD space, so it's 5 points in here. This is the origin, this blue cross, and I have a convex function h. Actually, this convex function h is the connected, not exactly, but connected to the the log partition function for the parameter, which we know it's convex. And our task, what we are going to do is to take two of those points whose sum maximizes this convex function h, and we want to prove that those 2 points are linearly separated from the others. Okay, so I'm going to say that if I find 2 points whose sum maximizes this convex function h, they are separated linearly from the others. So the graphical proof goes as follows. Okay, so in yellow, those are every possible sum of 2 black points. For example, this yellow point is a sum of these 2 black points. This is a parallelogram here. So yeah, my goal is to find the yellow point which maximizes this convex function. And because this function is convex, I know that I can restrict myself to the convex hull of those yellow points. So I obtain a multi-dimensional polyhedra. And because it's a convex function, I know that its maximizer is a vertex. The maximizer is the vertex of this convex function. Okay, so I have a vertex of a polyhedra, and I know that this vertex can be characterized as a point which is the furthest in some direction. This is the direction. And now coming back to my initial problem, how to find 2 points whose sum is the maximum in this direction. Well, obviously, this is the sum of 2 points which are themselves furthest in that direction. Okay, so it's easy to find a linear curve that separates those 2 points from the others. So this was quick proof of that that result. Now, coming back to this induced partition problem, the partitions that obtained firstly by partitioning the observation space and then taking a prior, computing the prior approximate expression for the prior weight. Well, this is what was before for the Gaussian CRP model with the same covariance for every cluster, and this was straightforward computations. In general, it's not that it's simply a computation. You actually do some analysis in here. It doesn't change that this expression, no matter what exchangeable random partition prior you take in the limit, you obtain this entropy path. And this is what you obtain from this conjugate exponential likelihood. This C star is the convex conjugate of the log partition function for the parameter. And now, actually, both of these limits can be viewed as instances of the following problem. So I have a sequence of functions fn which pointwise converges to function f. And what I want to prove is that nth norm of the function fn, it converges to the supremum norm of the function f. So if it weren't for this n, this is a well-known standard result that the nth node converges to the supremum node with some assumption. And if you put n in here, you need to do some additional estimation inequalities. Okay, so for the specific examples, this is what you've already seen. This is this delta function for the fixed covariance CRP model. If you allow the covariance to be sampled independently for each cluster from a Wishart distribution, it changes in such a way. This is the expected value of the logarithm of the determinant of the conditional covariance matrix conditioned on the observations being in. Apologies, in here it should be, those expectations you take with respect to P, and in here those covariance matrix you also take with respect to this P distribution. And now we, as I mentioned before, we for us was important the maximus of this function. This is the possibilities of the observation space. So I mean, it is difficult to analytically compute a partition of the observation space which maximizes such an expression. But the only case in which we were able to prove it, I mean, to find it analytically, was the case of the input distribution being uniform on the 0-1 segment. So in both cases, you are able to prove that the partition that maximizes these expressions need to be the one that you expect, in the sense that consists of different subsegments. You cannot have this segment and this segment in one component within the maximizers. Every segment, creates a different component. And now, for the if you know that, then it boils down to the analysis 1 exercise. Find P1 to Pn, which maximizes these expressions. So for the fixed covariance case, it turns out that you need to obtain equal lengths. So it's kind of symmetric, which is nice. This is what you expect, and you are glad that it is so. And another thing you are glad that it is so is that actually in the maximizer, those lengths are such that the segment variance is the one that approximates this theoretical one, the one assumed by the model, as close as possible. So you may not be able to give the exact value of this variance, because I mean, you've got a discrete space of possibilities, but you get the one which is as close as possible to the theoretical ideal. But for the latter case, this is much simpler, because it turns out that no matter what division into subsegments you choose, you get the same value of the objective delta, which is, I mean, easily computed, which was kind of surprising for us, and we treated it as a kind of disadvantage of the MAP approach in this model, in the varying covariance model, because we expected, I mean, we don't have proof of that, but we expect that because of that, the part, if you feed your MAP machinery by a random sample from the uniform, in this case, you won't have a stabilization. You will have a change in number of clusters. And this is what prompted us to give some additional information to this wishart. I mean, in general, this wishart has 2 parameters, and after some reparameterization, you can think that, okay, this is one of them is the expected value of wishart, expected matrix, say, so this is the covariance structure you expect in the component, and the other is the concentration around this expected value. So in order to kind of balance the fact that apparently in the standard wishart approach, as far as the MAP goes, the model is able to adjust too much to the covariance structure in the components, we allowed to this concentration parameter to grow linear with the number of observations. So we have some coefficients with some coefficients. So as the more data you get, the more your expectant value of the covariance structure within cluster is concentrated around this critical part you assume. And well, with this model, first we were able to kind of mimic one of these results from the very beginning, namely the one that you can control the cluster size cluster proportion that intersect a given ball. I mean, but unfortunately, even in a more restricted setting, namely you assume that actually the whole data set is bounded. I mean, although you've got infinitely many points. All of them are within some ball. But yeah, within this context, we are able to prove that in this model, this adjusted model, when you adjust the concentration coefficient linearly, the sample size grow linearly, not the sample size, but the size of clusters in the MAP partition grows linearly with the number of observations. And I mean, this not pleasant expression is what we get for this delta function for this adjusted model. And now this is already known. It was before. I mean, in here, what changed, the basic thing that changed is that instead of simply the covariance matrix within a set component, you get a convex combination of what you should have in P distributions and what you assume in the model. Apart from that, you get a kind of linear penalty for the number of components. And finally, this is a constant. Okay, so I mean, I see that I should approach the end of the presentation. So I mean, it's not surprising that actually by varying lambda, you have a continuous transition between the delta from the normal fixed covariance and normal Wishart covariance models. And this final application idea I'd like to give, I'd like to end with is the following. Okay, I have this function, and I know that it should somehow be connected to scoring function. I mean, from the model, scoring partition. From the model, I can expect that maybe the higher it is, the better the partition is in terms of my modeling assumptions. So the idea is to use empirical equivalent of that one to score clustering proposals, but given by different well-known clustering procedures like k-means. Okay, in k-means, you have actually several clustering proposals depending on the k parameter, how many clusters you want to have. And we are thinking that okay, let us see how this scoring function behaves as a way to choose among clustering proposals of other clustering methods. Okay, so yeah, this is an example of a data set I applied a k-means to. So those are different outputs of k-means depending on k. And for every such partitions, I computed this delta score and for a variety of lambda. And I mean, in here we can see that, I mean, this is not a promising picture, because although the maximizers of delta functions has 3 or 8 clusters, in here we had 5 clusters. So it's a bit disappointing that in here we've got like the only point at 5 clusters in here. But if you look closely, you can see that this k-means propositions for 5 clusters was a bit disappointing too, because it wrongly joined these 2 clusters and wrongly split this 1 cluster. So what we did is compared these delta outputs with what we know about the ground truth. So what you have on this gray background is an information about how this k-means proposition is close to the ground truth in some sense. And I mean, what we obtained from our simulations, not any results in this case, but we saw that actually there was always a range of lambdas for which it chose a good number of clusters. So for really large lambdas, usually it overestimated. For small lambdas, it usually, I mean, underestimated, but there was a range of lambdas. I mean, it performed reasonably. Of course, you can ask, okay, so how to choose the lambda? I was the initial task was how to choose k, so now I replace the problem with how to choose lambda, and it's a good point. But actually, this allows us to represent the whole thing graphically. So I mean, of course, there are other ways, some of them graphical as well, to choose the number of clusters in the k-means algorithms, like elbow methods. But yeah, this is another one in this vein. Okay, to sum it up, I mean, what in this presentation, what happened? I presented the results of this Bayesian analysis paper, where we showed linear separability of clusters in the Bayesian mixture model, and some results about how the MAP behaves in the limit. We showed what we are able to generalize in terms of more general models, and very, very briefly discussed some possible applications of a byproduct of this analysis. So thank you very much for attention, and if there are any questions, I'm happy to answer.